And thank you so much for being here. My name is Marjia, and I'm a final year computer science student and an AI safety researcher. And today I want to talk about something I think deserves a lot more attention, especially as we build more capable and autonomous AI systems. We're giving these systems increasing amounts of control to make decisions, take actions, and even coordinate with each other in the real world. And that raises a very important question. How do we make sure they behave as expected, especially in situations we didn't fully anticipate? That's what this talk is going to be about. Runtime safety for autonomous systems. How we can catch and prevent things from going wrong while the system is running. Alright, so let's address the elephant in the room. When we talk about AI safety today, most of the conversation focuses on filtering. We filter inputs to make sure people aren't asking AI to do bad things. We filter outputs to catch harmful responses. And we also have some edge case filtering to handle the weird stuff. And that's really important. We really need those safeguards. But here's the thing. As AI is getting more autonomous, there's a whole new category of problems that filtering just doesn't catch. Think about it this way. Filtering is like having a bouncer at the door at the club. They check your IDs, they make sure nobody's bringing anything that could cause harm, and they keep out obvious troublemakers. That's great. But what happens when people are already inside? What if two groups start causing problems together? What if someone makes a bad decision in the moment? That's what we're missing. We're not watching what happens when multiple agents coordinate with each other. We're not monitoring the decisions agents make right before they execute them. And we're definitely not prepared for emergent behaviors, those unexpected things that pop up when complex systems interact in ways we didn't predict. And this is becoming a very big deal, as multi-agent AI systems are becoming the norm, not just the exception. We're deploying teams of AI agents to handle things like customer service, manage infrastructure, analyze data, and they're all making these decisions in real time. Let me paint you a picture. Imagine you have 5 AI agents working together. Maybe one's handling customer emails, another's managing inventory, a third is processing refunds, and so on. Each agent on its own, that's pretty straightforward. You can predict what it'll do, or at least try your best to. You can test it, and you can feel reasonably confident about its behavior. But when you put them together, something fascinating and frankly a little scary happens. They start interacting in ways you didn't program or anticipate. So here's an example. You've got agent A, and it decides it needs to fetch some data, some user data from an API. Makes sense, right? It's doing its job. At almost the exact same moment, agent B arrives, which is working on a completely different task, also decides it needs the same user data. And it's also perfectly reasonable for it to do so. So what happens? Both agents hit the API at the same time, duplicate requests, and there you have it. You've hit your rate limit. Now, is either agent doing anything remotely wrong? No, they're not. They're both just trying to do their jobs. The problem is that they don't know about each other. There's no coordination layer saying, hey, agent A, just requested this data, maybe you should wait, or let's share this data between you two. This is going to start happening in production systems, and it's frustrating because it's not exactly a bug in any individual component. It's a bug in the system as a whole. Here's another one. Agent A is doing some cleanup work. It sees this file called temp_data.csv sitting there, taking up some storage space. So it thinks, this is temporary data. It's been here for a while, so let's delete it and free up some space. And that's a totally logical decision for it to make. Meanwhile, agent B could be in the middle of running an analysis, and guess what it needs? That exact same file that agent A is trying to get rid of. Agent B is counting on that file being there in order for it to accomplish its task. So while agent A goes ahead and deletes the file, agent B is in the middle running an analysis, trying to access it. And then the whole pipeline fails. You get error messages, alerts going off, someone's probably going to get paged at 2 a.m. to figure out what exactly went wrong. Again, neither agent did anything unreasonable on its own. The problem is that they had no visibility into each other's dependencies. Agent A didn't know that Agent B needed that file, and vice versa. This is what I mean by cross-agent dependencies. In a single agent system, you can usually track what depends on what, but when there's multiple AI agents involved, these dependencies cross boundaries, and suddenly they start to become invisible. So what could a potential solution be? This is where runtime enforcement comes in, and I think it's an approach that could become a reality quite soon. The core idea is quite simple. We put a checkpoint between when an agent decides to do something and when it actually does it. Think of it like this. An agent makes a decision, checkpoint evaluates that decision, and only then do we execute. It's like having a referee in a sports game. The players are out there making split-second decisions, but the referee is watching to make sure nobody breaks the rules. And more importantly, the referee can blow the whistle before something bad happens, not afterwards. I think this is a huge shift in mindset towards creating safeguards for AI. We're not waiting for things to go wrong and then trying to fix them and analyze the damage afterwards. We're catching potential problems before they turn into actual problems. And here's the really neat part. We can do this without changing how the agents themselves work. We're not rewriting their core logic. We're just adding this safety layer on top. So let's talk about what makes runtime enforcement different to filtering at the moment. Filtering is static at the moment. You set up your rules and those rules checks the inputs and outputs. That's it. It's like having a checkpoint that only checks your bag when you enter the building. Runtime enforcement is designed to be dynamic. It's monitoring decisions as they happen. It's enforcing policies in real time, and it can intervene mid-execution if something starts to go wrong. So we're not just checking what goes in and what comes out, we're watching the whole process. We're monitoring every decision an agent makes, such as when it decides to delete a file, when it makes an API call, and when it sends an email. And we can intervene while things are happening. If we see agent A about to do something that could conflict with agent B, we can stop before it causes a problem. So this is a very basic architecture on how such a thing could work. So there's three main components. So first, there's the agent core logic. This would be the existing agent that you decide to use. The thing that's already working, already deployed, and already would do the jobs for you. We don't touch this. This is really important because it means you don't have to write everything from scratch. Second, there's the safety wrapper and the policy engine. This is the new stuff that would be added. The wrapper intercepts actions before they execute, and the policy engine checks those actions against those safety rules. And then finally, there's safe execution. If the action passes all the checks, it gets executed, and if it doesn't, then it gets blocked. The beauty of this architecture, in my opinion, is that it's quite modular. You can plug it into existing systems without major refactoring. You can update policies without touching agent code, and you can add new safety checks without breaking existing functionality. So this is some code, the next couple of slides will have some, but this first one will be, I know you guys are probably thinking that's all great in theory, but is it actually practical? How hard would it be to implement? So this approach, as I mentioned before, would work with any agent framework, such as LangChain, AutoGen, Crew AI, any popular frameworks you have out there. It wouldn't matter. The safety wrapper doesn't care about the implementation details of your agent. Let me show you what the code could actually look like. You can create your agent however you normally would, and then you would import the safety wrapper, wrap it around your agent, load the policies, and then you run it. Just 5 lines of code. No changes to your agent's core logic, no refactoring your entire code base, no rebuilding from scratch. This is what I meant by it being a drop-in solution. You can integrate this into existing systems in minutes rather than months. And because it's framework agnostic, you can use the same safety layer across different types of agents in your system. Maybe you have some agents built with LangChain or others built with custom code. Same safety layer would work for all of them. This dramatically reduces the barrier to adoption, which I think is very important in our time right now with how fast AI is developing. The best safety mechanism in the world doesn't matter if it's so hard to implement that nobody ends up actually using it. So let's take an example of how the monitoring would work. So when an agent makes a decision, we would intercept it and log everything we would need to know. We would capture the agent ID, so what agent is actually doing this action. We capture the action, so what it's trying to do, and then we capture the parameters. So what are the specifics of this action? And we would log all of this context, timestamp what else is happening in the system and what dependencies might be involved. This gives us a complete audit trail. If something goes wrong, we can trace back exactly what happened and why. But more importantly, it gives us visibility. We're not waiting for something to break and then digging through the logs to see where it all went wrong. We can see potential problems as they're developing. So once we're monitoring decisions, we need to actually enforce our safety policies now. This is where the policy engine comes in. When an action gets intercepted, we check it against our rules. Does this violate any safety policies? Does it conflict with what other agents are doing? Does it exceed resource limits? If there's a violation, then three things would happen ideally. First, we'd block the action and it wouldn't execute. The agent would try to do something, but it would ultimately be stopped. The second would be alerting someone, such as an admin. Someone would need to know that this has happened, especially if it's a pattern that the agent is repeatedly doing. And then third, we would log this. It would go into an audit trail that can be analyzed later, look for patterns, and maybe update the policies when needed. The policy engine can be as simple or as sophisticated as you need it to be. You can start with basic rules, such as don't delete the files that other agents are using, or don't exceed API rate limits. As you learn more about how your agents behave, you can add more nuanced policies. And because these policies are separate from the agent logic, you can update them without redeploying your agents. If you end up finding a new edge case, add a new rule. No code changes required. So here's where it gets really interesting. What do we actually do once we detect a violation? The safety intervention has 3 steps, and they happen in order for a reason. So the first is that we prevent the action, and this would be the most important step. There's no point having runtime enforcement if we can't actually do anything about it in regards to preventing it. Whatever the agent was trying to do, we would stop it from happening. The API wouldn't go through, the file doesn't get deleted, the email doesn't get sent, and your cloud bills don't get racked up. Second, we would log the incident, and these aren't just for compliance or auditing, though it's also very valuable for that as well. It's so that we can learn from what happened. Maybe this would reveal a gap in how our agents are coordinating. Maybe it shows us a policy that we need to add. Third, we would also trigger a fallback. We don't just block the action and walk away. We try to do something safe instead. Maybe instead of deleting that file, we archive it. Maybe instead of making that API call right now, we queue it for later. Maybe we prompt the agent to try a different approach. This is what I mean by graceful degradation. The system keeps working, just in a much safer mode. We're not crashing everything just because one action got blocked. This maintains operation while preventing harm, which is exactly what we'd want in a production system where multiple AI agents are running. So let me walk you through the full flow one more time, because I think seeing how all of these pieces connect is really valuable. An agent decides it wants to do something, maybe it's a risky action, maybe it's perfectly fine. At this point, we won't know. That decision goes through the safety layer. The policy engine evaluates it. Does this violate any rules? Does it conflict with what other agents are doing? Could it cause problems? If everything checks out, great. That action executes normally. But if there's a problem, we intervene. We block the action, we notify someone, we log what happened, and we trigger a safe alternative if one were to exist. And this would happen in a few milliseconds. The agent doesn't just sit there waiting for minutes while we do safety checks. It's fast enough that it doesn't significantly impact performance, but thorough enough that it catches real problems. And the great thing about it is, this works the same way whether you have 2 agents or more than that. The pattern scales. So let's zoom out for a second and think about the bigger picture. We already know by now that AI can be a big black box. So imagine you have 5 agents and each one is making 100 decisions per minute. That's 500 decisions per minute flowing through your system. 500 opportunities for something to go wrong. 500 interactions that might create unexpected outcomes. And here's the thing. You just can't possibly monitor all of that manually. You can't sit there watching logs scroll by and spot the patterns in real time. The scale is simply too large. This is why multi-agent AI systems are becoming black boxes and even more opaque than single-agent systems. There's just so much happening inside them that it becomes effectively impossible to understand what's going on without serious tooling. And without visibility, debugging becomes a nightmare quite fast. something breaks, and you're trying to reconstruct what happened from partial logs, trying to figure out which agent did what and in what order. This is why runtime safety isn't simply about preventing bad things. It's about making these systems comprehensible again. It's about being able to see what's happening and understanding why. And this is where the model context protocol becomes really valuable. MCP gives us a standardized way to track what agents are doing across all of their tools, whether an agent is making API calls, reading files, querying databases, whatever you might think of. MCP can log all of it in a consistent format. This solves a huge problem that's going to happen with multi-agent AI systems, fragmented logging. Different agents might use different tools, different frameworks, different logging formats. Trying to piece together what happened becomes like trying to read a book where every chapter is written in a different language. MCP would fix this. Now we have one unified log of everything that happened. We can track complete execution steps from start to finish, and we can see what an agent decided to do and why. And this would also enable effective post-hoc analysis. After something goes wrong, and even if something goes right, we can go back and understand what happened. Why did these 5 agents coordinate successfully this time but fail that time? We could look at the logs. And the difference is that in the successful case, Agent A waited for Agent B to finish before starting its work. In the failed case, they both tried to do something at the same time. That kind of insight is incredibly valuable for improving your systems over time. So let me show you an example of such a thing. So here's an example decision log from a multi-agent AI system. So at certain times, Agent 2 decides to make an API call to fetch user data, and then 33 milliseconds later, Agent 1 decides to do the exact same thing. And then the system blocks the second request because it would exceed the rate limit. Now look at how clear this is. We can see exactly what happened, exactly when it happened, and why it got blocked. There is no ambiguity and there's no mystery. Without this kind of logging, you might just see rate limit exceeded and have to guess what caused it. Was it one agent making too many requests, multiple agents colliding, something else entirely? With MCP, it becomes more obvious. This is what I mean by making multi-agent AI systems be debuggable. We're trying to take something opaque and trying to make it more transparent. So here are some things that you guys have learned over the past few slides. So the first is that performance overhead for such a thing would be manageable. We were worried that adding the safety layer could significantly slow the entire operations down, but in practice we're talking about 2 to 5 milliseconds of additional latency per action. And that's nothing in most contexts. Your users wouldn't notice it. The second lesson is, policy design is harder than implementation. Writing the code to enforce policies is pretty straightforward, but figuring out all the different types of policies that your agents need to adhere to, I would argue that's the more hard part. And you also have to think about all these different edge cases. You have to balance safety with functionality. Too restrictive and your agents just won't do their jobs. Too permissive and you're not actually preventing problems. This is where good data about agent behavior becomes very important. You need to understand what your agents are actually doing before you can write good policies for them. And third, false positives need tuning. Initially, when I was making this tool, we were blocking a lot of actions that were actually fine. The policies were too aggressive. We had to dial them back, add more context awareness, and get more sophisticated about what actually constitutes as a risk. And developer adoption requires minimal friction. If this is hard to use, people just won't use it. And that's why I'm focused on making it a drop-in solution. The easier it is to integrate, the more likely people are to actually adopt it. And finally, and this is pretty obvious, but traceability builds trust. When people can see exactly what the safety layer is doing and why, they trust it more. Transparency matters. So I'm going to be really honest with you, we don't have all the answers yet. There's still a lot more work to be done in this space. And one of the big challenges is defining what exactly safe means in context-dependent scenarios. What's safe in one situation might not be safe in another. How do we build policies that understand context well enough to make those distinctions? Right now, we're relying a lot on human judgment to set these policies, but as systems get more complex, that'll arguably be harder. We need to be better at automating how to learn such safe behaviors in different contexts. The second challenge is scaling to systems with 10 or more agents. I've tested this with upwards of 5 or 6 agents, but when it's 10 or 20, at some point the complexity might become too much even for a runtime safe enforcement to handle it effectively. And more research needs to be done on how these systems behave at scale. And third is balancing autonomy with control. This is as much of a philosophical question as it is a technical one. How much control should we exert over agent behavior? At what point does its safety enforcement become so restrictive that we're actually undermining the whole point of having autonomous agents? There is a trade-off here, and I think at the moment we haven't figured out what the right balance is yet. So as we wrap up, I would like to leave you with 3 things to remember. The first thing is runtime safety catches what filters might miss. Input and output filtering is absolutely necessary, but I think in the world of AI agents, it's not sufficient. Second, non-invasive layers preserve flexibility. You don't have to build everything from scratch. You don't have to choose between safety and agility. You can add safety without breaking what already works. And third, MCP makes multi-agent AI systems a lot easier to debug. Having standardized, comprehensible logging transforms these opaque black boxes into something that is a bit more understandable and gives us the ability to improve on. So that's all I've got for you today. Thank you so much for your attention. So on the left, there is a form to join an AI safety organization that I'm currently building with someone. And I'd love it if you guys would like to be involved. And then on the right, if you'd like to connect with me on LinkedIn, feel free to do so. Thank you again, everyone.